All right, let's get back to Earth and talk about a new tool, sort of a new little piece of formalism for describing probabilistic events, which is called a random variable. So a random variable is a function from the sample space of some experiment to the real numbers. And that's basically all it is. So where S is essentially a probability distribution. So S is the sample space of a probability distribution. And random variables are usually denoted by a capital X, or sometimes capital Y, or capital Z, but most often capital X. And we write probability that X equals R to mean the sum over elements of S that X of S equals R, probability of S. So I want to take a minute here to say that personally, I think random variables can be a little bit confusing. So I want to take a minute to stop and work out any possible confusion from these definitions. So first of all, the words random variable can be accused of being slightly misleading. A random variable is a function from some set to the real numbers. In that sense, it is neither random nor a variable. But the name random variable makes some kind of sense because you can think of it as sort of modeling in some way a random variable, a random occurrence, because S is a probability distribution. So you can think of it as something random in that sense. And second of all, this notation is a little bit strange. It's the kind of thing that I normally would call a type error, because some of you have heard me use those words. But a type error is when you use words or symbols to describe something that does not match the type of object that it is. So for example, writing X is equal to R, here R is an element of the real numbers. So it doesn't make sense to ask if X is equal to R because X is a function and R is a real number. And so this kind of comparison doesn't actually make sense. But this is the standard notation for this thing. So we'll go ahead and use it. It's not the end of the world. And in fact, again, it makes a little bit of sense because if we're thinking about X as a random variable type of thing, what is the probability that X takes the value R? Well, it is just basically the probability that you have chosen something in S that corresponds to that value. That's what this summation is. You're summing over all the elements of S that map to R, and then summing up all those probabilities. So you're basically measuring the probability of the event that is the subset of S that spits out R under this function. So there's a little discussion of what a random variable is and does. Hopefully that made it less confusing and not more confusing. But if you're ever confused, then I encourage you to return to these definitions and work from the definitions. Think of it as a function on the sample space of a probability distribution, and remember this definition of what it means to write P of X equals R. So, with all that said, let's see an example. So let's flip a coin, and let's say it's a fair coin. So fair meaning probability of heads is a half and tails is a half. So flip a fair coin 3 times. And count the number of heads. So we can model this as a random variable in the following way. So remember, a random variable is going to be a map from s to the real numbers, which will denote x. And in this case, s is the set of strings of 3 h's and t's. So I'm going to write all of those down. Not too long. There should be 8 of them, I think. There we go. And so x, to each outcome in this set, x is going to associate a real number. And the real number that x is going to associate is just the number of heads in this sequence of flips. So this guy is going to go to 3. These 3 are all going to go to 2. These 3 are all going to go to 1. And this one is going to go to 0. So this is an example of a random variable. It is the random variable that is counting the number of heads in 3 flips of a fair coin. So what is the probability of exactly 2 heads which we write as p of x equals 2. So this is equal to, remember, the sum over s in s such that x of s equals 2. So essentially we're looking at the pre-image of 2, and we're summing up the probabilities over all those elements of the sample space. And in this case, the sample space is a uniform distribution with 8 elements. Oops, forgot to finish writing that. So in this case, it is 1/8 for heads, heads, tails, 1/8 for heads, tails, heads, 1/8 for tails, heads, heads. And that is all of the ways. That's all of the things that map to 2. So it's equal to 3/8. And in fact, so there is a relationship between random variables and distributions. In addition to the fact that a random variable is a function on the sample space of a distribution, we also have a random variable produces a new distribution. So remember, what do we need to write down a distribution? We need a sample space, first of all, and we need a probability for each element in the sample space. So in this case, the sample space of this distribution is x of s, which is the image of x, which we're thinking of as a function, which we have defined as a function. So this is just the image of that function. And for R in this image, the probability of R is what we defined before as the probability of X equals R. So you can check that if X is a random variable, then this set with these probabilities forms a distribution. And in the example above, so let me bring it back into view. So in this example, so distribution of X the sample space, X of S, that is the image of X, is these guys. So it's 0, 1, 2, and 3. And sort of just from looking at this map, we can see that P of 0, there's only one preimage, so it's 1/8. P of 1, there are 3 preimages, so that probability is 3/8. And same with P of 2, as we saw, is 3/8. And P of 3 is 1/8, because again, it has one preimage. And we can recognize this as a binomial distribution. So the number of successes in 3 Bernoulli trials with success probability 1/2, which is exactly what we should expect because we're measuring the number of heads in 3 flips of a fair coin. That's exactly the kind of thing that we were talking about being a binomial distribution before. So this random variable X is basically just another way of encoding this data. And it gives us, as we would expect, the familiar binomial distribution. But working with random variables just gives us a little bit more flexibility and generality, and it will be important for talking about expectation and variance tomorrow.